Welcome back to the channel, everyone. In this video, I'll try to explain the questions that appeared on the IB May 2022 Physics High Level Time Zone 1 multiple choice paper. Because of copyright reasons, I don't think I can show the actual paper. Instead, I have paraphrased all the questions on this Google document. I will add my own annotation, and I hope the explanation that I will give during the video will be satisfactory. Of course, I still hope you guys have an actual copy of the paper from your teachers or from some other legitimate internet sources. So without further ado, let's just get started with the first question, which is about figuring out the SI unit combination for the quantity intensity. The question does tell you that intensity equals the power over area, even though this equation itself is given in under topic 8's formula book. So to figure this out, what you have to do is to break down the more complicated SI derived unit or derived units into simpler derived units and ultimately as SI fundamental units. So we'll begin by writing I equals to P over A, power over area, which is what that question provides. Power in turn should equal to energy over time. You can write work done, you can write energy, but the units are going to be the same. I'll just write energy out explicitly. If you write E, you may confuse E with some other quantities like electric field or voltage. T, I think T is unique enough. And the energy, in turn, has to be broken down into something even more fundamental. You can use force times distance because work done equals to force times distance. I prefer to use half mv squared kinetic energy because mass and velocities are both very intuitive quantities. So the unit would equal to kg. So the m here is actually the quantity symbol as opposed to the unit symbol. And you can ignore the half in front because the half has no units. V is velocity, so meter per second. With the square, it will become m squared s minus 2. Area itself is m squared, and the time is s. And then you can just clean up the units, recognizing that the meters actually cancel perfectly. The times s to the negative 2 divided by s is s to the negative 3. As a result, D would be the correct answer. Moving on, second question. The magnitude of the resultant of the two forces acting on the body is 12 newtons. And then they are asking which of the four choices can give rise to the resultant of 12 newtons. And what you guys need to be aware of is what happens when you combine two vectors in unspecified directions. In the case where you have got two vectors acting on the same object, or two force vectors acting on the same object, the maximum resultant is the simple sum, and then the minimum resultant should be the simple difference. And then any other in-between magnitudes are possible as long as you angle the two forces properly. So looking at the choices, choice A is definitely not correct, because if you have 1 and 2 cooperating, the maximum resultant that you can get would just be 1 plus 2, which is 3. Choice B, the maximum is 15, but the minimum is 13, because 14 minus 1 is 13. So no way you can achieve a resultant of 12 using those two forces. Choice C suffers from the same drawback as choice A, because 5 plus 6 is 11, and that's the best that you can do with those two forces lining up properly. And then finally, 6 and 7, they act in the same direction, then you get a resultant of 13. To get a resultant of 12, what you can do is to angle the two forces in a way. Actually, the arrow is a little bit off. So that when you complete the vector triangle, the magnitude of the resultant becomes 12. And you can figure out the angle between the two vectors by using some trigonometry, like such as cosine rule or sometimes sine rule. But the use of sine and cosine rules are not part of the physics syllabus. Well, I guess you guys still need to know this for math, so you guys can practice figuring out the angle in preparation for your math papers. But for this particular question, it's enough to recognize that 6 and 7 would be the pair of forces that, when angled properly, can give you a resultant whose magnitude was 12. So the answer is D. Moving on, question 3, which asks for the percentage uncertainty in the temperature difference or change in temperature. If a liquid cools from 20 degrees to 10 degrees Celsius. Both temperature measured using a liquid in glass thermometer with a 0.5 degrees uncertainty. So the temperature difference is simply 10. And in a subtraction situation, you guys should recognize that the uncertainty of the calculated quantity is the simple sum of the absolute uncertainties of the two starting quantities. So 20 minus 10 is 10, and then 0.5 plus 0.5 is 1. So the percentage uncertainty is just 1 divided by 10, and then you multiply by 100%. And that should be a very obvious 10%. So choice D again. Not the most difficult uncertainty calculation out there, but it's always nice to have a fairly easy toss. Question 4 now is about some, you can either use force like Newton's laws plus Zuvat to figure out a question like this. So a block moving with initial speed brought to rest after some stopping distance of d and frictional force F, and then you repeat the experiment using a different starting speed and halve the frictional force in bringing the object to a complete stop, and then they ask you to relate the two starting speeds. I mentioned about Zuvat and kinematics or Newton's laws. Turns out I think friction using work energy will actually be a faster approach as long as you recognize that the work done by a frictional force will correspond to a decrease in kinetic energy. So force times distance equals to half mv squared, and I'm using this in fraction format. So just writing the same equation again, but using your new set of quantities. And then recognizing that a whole bunch of quantities cancel, that frictions cancel, distances cancel, halves cancel, masses cancel. And if you rearrange this, you just end up with u squared equals to half v squared. And then finally, you can just take the square root. U equals to 1 over root 2 times v, making b the correct answer. Now moving on, question 5 turns out to be a fairly easy projectile question. They give you the height of a cliff. They don't give you the gravitational field strength. It turns out that's not needed. They give you a starting speed, and they even give you the time, because typically what you have to do is to use the vertical motion. You use the vertical acceleration to figure out time of fall using something like s equals to half at squared. And then you use the time that you calculated to figure out the horizontal range using distance equal to speed times horizontal speed times time. But for this particular question, the time of fall of 2 seconds just means that the distance that the object travels from the base of the cliff, the horizontal distance is 1.5 times 2, which is 3. The question is actually asking for the magnitude of the displacement of the stone. So the stone has undergone diagonal motion. So it's just a matter of figuring out the length of this diagonal. And the simple application of Pythagoras should allow you to deduce that this diagonal is just 5. So choice B is the correct answer. Moving on, question 6 is an Atwood machine question, which does not show up a lot in past papers. What you should do is to consider all the forces acting on the individual masses within the system. So there'll be two weights, and I know that M1 is stronger than M2. Actually, no, I take it back. It's the exact opposite. M2 is stronger than M1. And this is apparent because they tell you that M2 is accelerating downwards. And there's also going to be tensions acting upwards. For this particular question, you don't actually need to involve tension. Other good habit, however, you should consider writing 3 equations, 1 for the entire system, and then 2, like 1 each for the individual objects. I'll write the equation for the system first. So equation of force, so it's an application of F equals to ma, a very simple looking equation, but then like re-representing the F within F equals to ma, which is the net force, as a vector sum and or difference of the forces acting on relevant masses is not something that students can master. It's not something that most students master, strangely. So for the system, you have M2G being a forward force. M1G is holding back the system. And then the two tensions are internal forces, and they are equal and opposite within the system. So they don't really affect the combined acceleration, well, the acceleration of the combined mass of the system. The question actually tells you the acceleration, which is half g. So expanding the right-hand side followed by rearranging. I think you end up with half m2g equals to 3 over 2 m1g. Canceling the g, canceling the half, and then dividing the 3 to the left-hand side. And then dividing the m2 to the right-hand side as well allows you to use that m1 over m2 should equal to 1/3, which is choice A. If the question asks you to figure out the tension, what you have to do is to write an equation based on either the m1 or m2 is fine. If you ever use m2, then you look at m2g minus t. So we cut off the system like this. So m2g and t are the forces that directly act on m2 only. So applying F equals m8, we have m2g minus t equals to m2a instead of m system A. With the acceleration that you calculated earlier, you can figure out t in terms of m2 and g, most likely. And you can set up a similar equation for m1. It's t minus m1g this time equals to m1a. And if you have done everything correctly, then the two t's should be equal and opposite to each other, as predicted by Newton's third law. Moving on for now, question 7. A book is resting on a table. There's no diagram provided, it's just pure description. Book is resting on the table, and they are asking you for the other member of the Newton's third pair, if the original force of interest is the weight of the book. So this is a very classic trap. Most students will be thinking along the lines of Newton's first law, because the weight of the book is intuitively supported by the table, which prevents the book from falling through the table. However, these two forces represent like a pair of Newton's first pair. Well, this demonstrates Newton's first law because these are equal and opposite forces acting on the same object. In Newton's third law situations, the two forces that are of interest need to be acting on different objects. Scrolling to the note section, so the two objects must be acting on different bodies. So the weight of the object, well, the reason that an object experiences weight is because Earth generates a gravity that pulls the object downwards. Turns out the object itself will also generate some minute gravity, but then this minute gravity acting on a massive object such as the Earth will generate an equal and opposite upward force acting on the center of mass of the Earth. And that's what choice A is about. So most people would have, like students who are unaware of this application of third law would have chosen the push of the table on the book as the support force, which explains how Newton's first law worked. But this question is about Newton's third law instead. So in any event, the question is A, the answer is A. Question 8 now. A car travels from rest along a horizontal surface with a constant acceleration, and they are asking you for how the kinetic energy varies with distance. They have a few graphs. They have this graph. They have a graph with different curvature, and they also have a graph with linear curvature. They also have a horizontal graph, but that's clearly not going to be correct. Ke is not constant because the object is undergoing constant acceleration. And notice that the horizontal axis is displacement and not time. So you have to resort to some equation to figure out the correct graph. So kinetic energy is half mv squared, famously. To relate kinetic energy to distance, however, you have to recognize that kinetic energy should equal to the work done by some accelerating force acting on the system. So knowing that Ke equals a half mv squared is actually not useful for this question. If they ask you for a graph of kinetic energy as a function of time, then half mv squared will be useful because you can replace the v within half mv squared as u plus at. So the Ke time graph should look like the first choice, but that's not what the question is asking for. The question is asking for the Ke distance or Ke displacement graph. And because constant acceleration is what's happening to the car, constant acceleration requires constant force. So you should have a graph with a constant straight diagonal line, so constant gradient. And in fact, you can further conclude that the gradient of the graph corresponds to the accelerating force. Either way, the choice is D. Question 9b, head-on collision of two identical masses. The initial directions of the spheres or of the masses. So this is what the diagram shows. Classic trap is for you guys to overlook the importance of keeping track of direction in a collision situation. Momentum is a vector, and the consequence of momentum being a vector is that when you have a collision situation during which the objects collide head-on, you actually need to subtract the magnitude of the momentum. So the momentum of the system is actually 8m minus 4m equals to 4m. And you guys just need to see which choices will also give rise to a final momentum of 4m. And the answer should be the second one, because 1m plus 3m is 4m. Choices C and I think choices A and D both correspond to answers that students can get if they overlook the fact that the 4 that was provided within the question should be designated a negative, should be associated with a negative sign. But for this question, the correct answer is B. There's some common collision situations involving identical masses, and just show you this. So a table summarizes common exam situations when you have identical objects traveling in equal and opposite velocities, that they would just bounce back with the same incoming velocity. And then there's also a situation where the two objects collide perfectly inelastically. So all Ke is lost in that case. And then there's also some other collisions when you have one object at rest undergoing being impacted upon by another identical object, and the collision is perfectly elastic. This is the case where the hitter will transfer 100% of the kinetic energy to the hittee. And then this last situation showed up in a, I think this last situation showed up in a multiple choice question within the specimen paper like 7 or 8 years ago. Moving on, question 10. A driver uses the brakes on a car to descend a hill at constant speed. What is correct about the internal energy of the brake discs? If this question is not about, it's just about energy conversion in general, then it is a GPE becoming heat energy situation. Descending a hill typically is associated with a gain in speed, but the question describes clearly that the speed of the object remains constant. So loss of GPE without a gain of Ke means that there must be some friction or resistive forces. And when these resistive forces act, mechanical energy of the system is converted into heat energy, thermal energy, internal energy, whatever. In topic 3, you have to distinguish between the 2 types very rigorously. Here, what you have to know is just that the internal energy of the system will increase, so the brake pads will warm, the surrounding air will also warm. But the answer should just be simply increase, which is choice A. Question 11 now, so this is about mixing. So they give you the properties of the 2 objects, their masses, the specific capacities, and the temperature changes. They want you to find the mass of Y in terms of the mass of X. So in a mixing situation, energy lost so change energy by the hot object should equal to the change in the energy by the cold object. because that's how energy conservation works. So I can write for x, which is x is actually the cold object, and I'll just write it on the right side. M times 2c times 6t minus 20 equals to y, which is whose mass is unknown. And if you just simplify everything else, or simplify everything, equals to the right hand side, you're looking at 40 times 2, so 80 mc. So the c's are gone, and then you can see that my equals to 4m, making choice C the correct answer. So make sure that when you guys use Q equals to MC delta T, you designate the temperatures so that the delta T is a positive quantity. It's way easier to just work with positive chunks of energy in general. Question 12 is about properties of an ideal gas. So they give you a graph like with a little bit more detail, but the key information to extract is the gradient is 400 divided by 50, which is 8. The units are actually tricky as well. The pressure is given in kPa, whereas the volume is given in standard units. So you're looking at P, well, PV equals to nRT in general, and they want you to figure out it's the number of moles of gas in terms of R. The y-axis is, the x-axis, my bad, is plotted as 1 over V. The y-axis is in kPa, whereas in general, the pressure within PV equals to nRT is just PA. So the gradient of this graph should be nRT. But what you have to do is to figure out whether there should be a multiplier of 1000 or whether you should be dividing the pressure by 1000. I think in this case, you have to divide by 1000. Which means that you have to multiply the right side by 1000. You look at 8 equal to n. No, wait, actually, I take it back. It should be multiplied by. You're given kPa, and then you want to convert kPa into PA. It should be multiply instead of dividing. So my bad. So this P is the P that is plotted on the y-axis for this particular question. So the gradient would equal to, so the gradient of this graph equals to nRT divided by 1000 instead. So 8 equals to n times R times temperature, which is given to be 100, all divided by 1000. So if we just multiply the 1000 over and divide the 100 over, you end up with 8000. I could just cancel the 2 zeros like this, maybe. That's faster. So look at 80 divided by R equal to the number of moles. Fortunately, there's no trap answer about like messing up the conversion factor of 1000. There's another choice A has 10 to the 5, which is a very big power of 10, but then the front number of 2 is just nothing like the 8 that you should be expecting. So the choices in the question are fortunately subtle and not such a nasty way that will cause you to fall for a trap. In any event, the answer is C. Now, question 30 is a tricky wave question. So a wave of period 10 milliseconds is traveling through a medium, and the graph shows the variation of the particle displacement with distance for the wave. The question asks for the average speed of a particle in the medium during one cycle. And a lot of students will just confuse this with the speed of the wave itself. So the difference between the two kinds of speeds is illustrated by this, well, that was animation. So when I press play, I'll just turn on the blue point. The speed of the wave is the speed at which the wave pattern moves from left to right. Whereas the average speed of a particle in the medium during one cycle, well, you have to focus on the purple spot, which is a point in the wave going up and down. you have to time one full oscillation, and then you have to see how much distance the purple spot would have moved through. I hope it is not too difficult to see that the distance that an oscillating point moves through during one cycle of oscillation is 4 times the amplitude. So the average speed of a point on the medium should be given by this equation. It's not given in the formula book, so you guys need to be able to interpret the question and not just fall for the obvious. So going back to the question itself. So the amplitude is 4 cm. So the amplitude is 4 times 4.0, all divided by the period, which is 10 milliseconds. The answers are all in standard units. So the speed is 16 meters per second, which is choice C. And notice that I did not even use the 20 cm, which is actually the wavelength. So in any event, hopefully, my explanation clearly illustrates the 2 different kinds of speeds that you can be asked about on a question like this. Now, question 14 now. An interference pattern with minima of 0 intensity is observed between light waves. So you've got 2 waves undergoing perfectly destructive interference, which must be true about the frequency and amplitude of the light waves. So it turns out for 2 waves to undergo destructive interference, they must be so-called coherent. Coherent just means that the 2 waves would always have some constant phase difference. And for 2 types of waves within the same medium, having a constant phase difference just means that they have to have the same frequency. The amplitude meanwhile has to be the same as well, because if the amplitudes are not the same, then you won't get perfectly constructive or perfectly destructive interference. So I do have an animation here that I spent forever making. The origin and the blue point are the sources. And I have picked an orange one. This point is, I can move this point around. Just go back to the original. So this orange point is barely moving. And if I change the amplitude of one of the waves, right now the amplitudes are both 10 arbitrary units. So if I make A to be like 4, you can see that the red wave has smaller amplitude, and then I have not changed the observation location. So it's still destructive interference, but then you can see that even when the 2 waves are destructively interfering, there's still an amplitude of 10 minus 4, which is 6. I guess you can't see 6 clearly within these illustrations. But I hope the idea that the destructive interference is not complete is evident. I'll show you what happens when you change the frequency of one of the waves as well. Change this back to 10. And if I change the frequency, and if you pay close attention to the orange spot, then you can see that the orange spot does not follow a simple like sinusoidal oscillation. It goes down, but it doesn't go down all the way to the bottom. It rises up a little bit and then it continues to fall. So you don't get the usual sine wave or cosine wave if you model the point. It's clear that the answer is C. First, close this first. Now, question 15. A beam of unpolarized light of intensity I0 is incident on the polarizing filter, and then you're rotating the angle of polarization on the filter. What would be the resulting graph like? Would you get a cosine graph, or would you get a constant intensity graph? This question is actually, I think this is supposed to be a trap question. Because what happens that if the initial beam of light is unpolarized, the transmitted intensity will exactly be half the intensity regardless of the orientation of the transmission axis. And then the cosine graphs will apply only when you begin with a beam of light that is already polarized. So there will be some question which involves an unpolarized beam incident on a polarizer and then an analyzer. In those cases, the cosine graph will then be correct. But for this particular question, but only one polarizer and a beam of light that begins unpolarized, you just get constant intensity regardless of the angle of polarization. So question of 15 is D. Question 16 now, standard two source interference question. So the question describes an interference situation like this. So there are two sources and there's a screen, and then there's a central maximum here, and then X up there is a minimum. It's a dark fringe, and then in between O and X there are two other dark fringes. Actually, I probably should draw it more nicely. And then they're asking you the path difference between the two beams of light arriving at point X. And if you guys are familiar with two source interference, you guys should be able to associate O and X with the central maximum, and then this other point on the pattern. And then this other point on the pattern is due to the waves arriving at the screen with 2.5 wavelengths of path difference. Like the first maximum path difference is 1 lambda. The second maximum, 2 lambda, and then there should be a third maximum somewhere over there. And then for the point X within the question, it should just be 2.5. And the answer is A, I think. Is it A? No, actually, the question 16. The answer is C, my bad. Now, question 17, statements regarding adjacent antinodes on a standing wave on a string. There are 3 statements. But before we analyze the 3 statements, so P and Q are adjacent nodes on, adjacent antinodes on the string. So the string pattern can look like this, maybe. They didn't mention about which harmonic, but then the harmonic number does not matter. I'll just draw 3. So P and Q are these locations. So clearly they're separated by half a wavelength, because this is 1 full wavelength, so this is half a wavelength. P and Q have a phase difference of pi radians. That's clearly correct, because every point within 2 consecutive half wavelengths separated by nodes, they will always be perfectly out of phase. Because when one point in a wave is going down, for example, all the other points on the neighboring half wave will be going up. And phase refers to the stage of oscillation of points on a wave. Now, the last statement is clearly wrong, actually, because there's no energy transferred between any 2 points on the standing wave. So I think A is a very clear, correct answer. Moving on to question 18. P and Q are point charges, and they indicated at P, number 1, the force acting on P, and number 2, the electric field at the location of P. And they asked you to figure out the corresponding quantities acting at point Q. Well, first of all, the field acting at P is outwards. That means that Q has to be a positive charge. And then P, meanwhile, is attracted towards Q, and that implies that P itself is negative. Now, using this information, you can figure out that the field at Q must be due to P, and since P itself is a negative charge, the field must be towards P. And then the force, well, electric forces must be like Newton's third law pairs. So that allows you to deduce that the force acting on Q should be towards P as well. You can also realize that a negative field, well, the field line acting on a positive charge, for which Q is, means that the force acting on Q should be in the same direction as the field. So either way, you should be able to deduce that both the field and the force on Q should be acting towards the left, making choice B the correct answer. Now, question 19, they have a triangular arrangement of point charges, and they are asking for the direction of resulting electric field at P, and this should be super straightforward because the geometry is very simple. You've got two positive charges upwards, and then remembering that the direction of field line is the same as the direction of force acting on a imaginary positive particle placed at the location. So all three fields have some downward component. Horizontally, the symmetry will cause the horizontal components to cancel out. So the correct answer should be clearly C, downwards. Question 20 now is a challenging question in the sense that they are asking for potential rather than the traditional potential difference. So potential at a point rather than potential difference across components. Still, you can analyze the potential difference across the various combinations. So before L was removed, this parallel combination should have a resistance that's half the individual resistances. Hopefully this situation you guys are familiar with it. When you have like two identical resistors in parallel, the effective resistance is just the individual resistance divided by 2. So you now have a 5 ohm, 10 ohm resistor in series situation sharing the 12 volts. If you have voltmeters connected across, this should be 4 and this should be 8. The potential at X, meanwhile, well, you have a source voltage of 12 volts. So the potential at these locations should all be 12. And then the parallel combination uses up 4 volts. So that should be exactly 8 volts remaining. At location X. Now moving on to the second half of the equation where you remove one of the resistors. You now have two identical resistors in series. So they're going to share the voltage evenly. 6 volts, 6 volts. And if the battery is still 12 volts, then after the first battery uses up 6 volts out of 12 volts, then you would have 6 volts remaining. So going from 8 volts to 6 volts, there will be a decrease in 2 volts at location X before versus after. So this is how you solve a circuit problem using potential instead of potential difference. Question 21 now is a interesting Kirchhoff's law situation. I'll show you the simple treatment when you have identical batteries in series. With identical batteries in series and the batteries having internal resistances, the treatment is like this. So the total EMF is the same as the EMF of one of the batteries only. And then the total internal resistance can be calculated using the parallel resistance formula. So this treatment is definitely not given in the formula book. How are you supposed to figure out this on the spot? Well, if you remember this rule, let's try to solve this problem within the rule, or with this rule only. So you can rewrite the circuit as a 5 volt battery with an internal resistance of only 1 ohm. There's 2 and 2 in parallel. Effective resistance only 1. The bulb still has 4 ohms of resistance. So this is now a simple series circuit with 5 volts serving a total of 5 ohms. So 5 divided by 5 is just 1, making A the correct answer. So what if you don't know the proper treatment? Well, you can still use Kirchhoff's law's ideas. So you have 2 batteries supplying a current of I, perhaps. So when the 2 currents merge at the junction and entering the battery branch, you will now have 2I. And you can now write the equation 5 equals to 2I plus 4 bracket 2I. This is the voltage loop, Kirchhoff's second law, the loop law. This is the source voltage. 2I is the potential difference across the internal resistance, and then the 4 times 2y is the potential difference across the bulb. If you continue to solve this question, I think you end up with 5 equal to 10I, and then I equal to 0.5. They want the current through the emitter, so you have to double that. So either way, the answer is 1, but I think the first approach is clearly faster. Question 22 now. So a conductor is placed in a uniform magnetic field. They give you the current, they give you the force. They want you to figure out the direction of the magnetic field. And then secondly, they want you to see how the magnetic force will change if you tilt the wire a little bit. The first part of the question should be straightforward. You can just use the left-hand rule. And if you orient your, there are many different versions of the left-hand rule on the internet, but the version that I use to teach students would be FBI. So if you, and make sure that you twist your wrist and don't change, and ensure that the 3 fingers remain mutually perpendicular to each other at all times. So current is my middle finger. I'm sticking it towards the right-hand side, and then the force, which is the thumb, is going to be oriented downward according to the question. I can see that the direction of magnetic field is acting out of the paper. Now we have to address what happens when you tilt the wire. So is this 30 degrees the angle that you use within F equals to EI L sine theta? For this question, the answer is no. This is actually a trap question. Even if you tilt the wire, the fact that the magnetic field is directed out of the pitch means that the current is still maintaining a right angle with the field. Right angle, theta equal to 90, sine 90 is 1. Therefore, the magnitude of the magnetic force is still unchanged, making C the correct answer. Question 23 now, hang on, there's some formatting issues. So they portray a vertical circular motion situation with a ball attached to a string with the quantities, relevant quantities shown here. Turns out this is just a simple application of mv squared over r. Because at this particular location, there may be some, well, the weight of the object is acting perpendicular to the tension. So the weight of the object may cause it to undergo vertical deceleration if it is ascending, or vertical acceleration if it is descending. But the weight has no influence on the centripetal force at this particular position within the circle. So here, the centripetal force is contributed by tension and only tension. Therefore, just using the centripetal force formula, you get a resultant, you get a tension force of 8 newtons. So that would be the result, at least the resultant centripetal force. There will be a tangential force most likely. Yeah, but for this particular question, all we care is the centripetal component of the resultant force, which is 8. Now, question 24. Question 24, the question is asking about 2 moons of equal densities orbiting a planet. The comparative quantities are all given or summarized in this table. What you have to do is to relate the 2 forces. You can use mv's, you can use, no, not mv squared, you can use gmm over r squared, my bad, because they're asking for force. Gmm over r without the square would be orbit kinetic energies instead. So the force exerted by a planet on Q again using F equals to gmm over r squared in fraction format. Well, let's see what cancels. So capital G for sure cancels. The mass of the planet cancels. I don't think anything else cancels, so I'll just rearrange. Our P should go on top. So the right hand side should evolve into this. So now what do we have? Well, RP is twice RQ. Meanwhile, P has half the volume, and if the densities are the same, then P has half the mass as well. So this should be a half at the bottom. So on the right side, you're looking at 2 squared divided by half. So that's 2 squared times 2, so 8. So F Q equal to 8 times FP, making D the correct answer. Question 25. A pure sample of iodine 131 decays into xenon with a half-life of 8 days. What is the number of iodine atoms remaining over number of xenon atoms formed after 24 days? So I'd like to use a chemistry approach. So let the original amount of iodine be X, and then that way half-life works. 24 days correspond to 3 half-lives. So when 3 half-lives have passed, only 1/8 of the remaining iodine remains. So 7/8 will be gone. And in a 1-to-1 conversion, the iodine that was sacrificed will all become xenon. So the ratio of iodine to xenon is just 1/8 over 7/8. So Brazil over Germany, I guess. So answer is B. Okay, question 26. Okay. They give you some energy levels. The diagram shows atomic transitions E1, E2, and E3 with when a particular atom changes its energy state. So basically, you're referring to electrons jumping around. And E1, E2, and E3 correspond to the energy of the photons released. The question in turn asks for a mathematical relationship between the 3 wavelengths involved. Well, it's very evident that E1 equal to E2 plus E3. You guys further need to recognize that photon energies are inversely proportional to the energy. And if you cancel the HCs, you can see that choice D will be the correct answer. The inequality is wrong. Energy is inversely proportional to wavelengths. So large energy gap means short wavelength involved. So D is the correct answer. Moving on, question 27 is about completing a nuclear equation, and this one is relatively straightforward. It's supposed to be a photon, and you guys need to recognize that the photon has no proton number and no Mach number. So all you need to do is fill in the atomic and mass number of nitrogen. So chemistry students probably know that nitrogen is element 7 anyways. And then the top number is just 13, given that there's no change in identity of any of the baryons or quarks. So 7 neutrons, actually no, 7 protons and 13 nucleons. The question, however, is asking for neutrons and not protons. So there's a bit of a trap. So neutron is 13 minus 7, which is 6. And the nucleons, I think nucleon has a symbol of A. So typically, the atomic symbol is like Z at the bottom, A at the top. So the nucleon number is just 13. So choice B is the correct answer. Question 28, a wind generator slows down wind from V to V/3 as the wind passes through the generator. For this question, you would just need to use the wind energy equation, which is given in the formula book. I should start writing first. So the power equals to 1/2 A density B cubed. And slowing down the wind from V to V over 3 actually extracts a lot of energy. So the P remaining of A density P over 3 cubed, and then a whole bunch of quantities cancel, halves are gone, A's are gone, densities are gone. You just end up with 1 over 3 cubed, which is 1 over 27. So if this is the wasted power, then the theoretical maximum power is just 1 minus this. Making choice D the correct answer. Question 29 now. So they give you a simple diagram which shows the incident intensity is 600 and then the reflected intensity is 150, while radiated intensity is 450. And they ask you for the albedo of the region. Knowing the definition of albedo alone should help you figure out the answer already, because albedo is the ratio of reflected intensity divided by incident intensity. And this actually means that the radiated intensity is actually not the same thing as reflected intensity. The radiated intensity has to be first absorbed by the surface material, and then the surface material warming up to a particular temperature will then re-radiate the intensity as its own black body radiation. The radiated intensity is just not part of the albedo definition. So the answer here is just 150 over 600, which is a quarter. So choice A is the correct answer. Question 30 is quite debatable. It's the only question that gave me trouble when I tried the paper myself. So how does doubling the slit width of a very narrow slit affect the central maximum intensity? I hope no one's going to have problems with the second part of the question, which asks for the angular position of the first minimum, because you have the famous formula book equation. Angle equals to lambda over b. And then angle, in turn, equals, actually, they're not even asking for the linear position of the swing. So then if b becomes 2b, well, b was x, I should say, x becomes 2x. Then the new position for the first minimum would just be lambda over 2x instead. So the issue is with determining the intensity of the beam, that the intensity of the central maximum of the profile after single slit diffraction. But when you add more slits, like in a multiple slit refraction situation, you have more constructed interference at the central maximum, and the intensity of the central maximum therefore follows the square law. Intensity is directly proportional to amplitude squared. If you simply widen the slit, there is no guarantee that every single source from the different location within the slit. So this is actually a pretty tricky situation that requires the formal treatment is super complicated, requiring calculus. But what happens when you just widen the slit is that you have more light traveling like towards the middle, and while you still have overall constructed interference at the middle, there's no guarantee that every single bit of light that comes from the slit will all cooperate and produce a constructed interference pattern. So you're not going to get 4i as a result. And if it's not 4i, then it just need to be 2i. So I think question 30, that's why the answer to question 30, the question 30 is B, although I have never seen this kind of question show up in any past paper. Question 31 now is about resolution. So an observer with an eye of pupil diameter D views the headlight of a car. Wavelength is lambda, and then the separation between the headlights is L. And they're asking for the greatest distance between the observer and the car. So I trust everyone knows to apply Rayleigh's criterion. The minimum resolvable angle equals to 1.22 lambda over D, and D is the diameter of the aperture. And not everyone knows the need to further relate the angular separation of the source with the linear separation of the source. What you have to do is to use trigonometry with small angle approximation and in radians. So this is a capital D is the distance that we're trying to find. So L over D equals the angle. And if you do some cross multiplying, you end up with small d times L over 1.22 lambda equal to the capital D that we're looking for, and that's choice C. And I'll just show you these equations that are not presented within the formula book. So theta equals to 1.22 lambda over B is in the formula book, but the extensions, which involve the use of small angle approximation and some trigonometry, is something that you guys should be aware of. Moving on, question 32. A charged sphere in a gravitational field is initially stationary between two parallel metallic plates, and they are asking you what could cause the charged particle to actually accelerate. So what's happening right now is that you have electric force equals to gravitational force in order for the particle to not go anywhere. And one thing that you guys need to further do is to rewrite electric field as V over D, where V is the voltage between the two plates and then D is the separation between two plates. And this is an important electrostatics equation, supposedly introduced under topic 5. It's actually quite, the most teacher or most student that I talk to are actually quite unsure whether this is actually needed for SL student as well. But yeah, you can see V equals to V over D. It's not given in the formula book, but it can be derived. So let's go back to the question for now. So if you now know that the electric field depends on the voltage and the distance, then you should be able to see that changing the V will disrupt the balance of the forces. Changing D will also disrupt the balance of the forces. Now it boils down to whether applying a magnetic field can also disrupt the force balances. And the answer to this question is no, because magnetic field can only generate cause a charged particle to experience a force when the charged particle itself is already moving in some direction that's not parallel to the direction of magnetic field. In this case, the charged particle within the question is actually at rest. So there's no way that the charged sphere can experience a magnetic force. So applying the magnetic field will not cause a disruption of the balance of the forces that the charged particle is experiencing. So the answer in this to this question is just A. Moving on, question 33. They're asking for the calculation of escape speed under a fairly trivial situation. Object of mass m launched from the surface of Earth, and the mass of the Earth is given by capital M. Radius is r, gravity is g, and they want you to write an expression for the escape speed in terms of small g. Well, first of all, the equation for escape speed is actually given in the formula book. It's derivable by considering the conservation of energy. For this particular question, you just need to recognize how to combine the escape speed equation with small g, which is gm over r squared. It's capital M, by the way. If you multiply one of the r's to the left-hand side within here, then you have gr equals to capital Gm over r. And all this within the escape speed expression or equation, the right side is now becoming just square root of 2gr. And turns out that's the correct answer. Moving on, question 34. The graph shows the variation of magnetic flux in a coil with time, and it's given to be a cosine graph. The graph looks like this, and I trust most students will recognize that this is the cosine graph. And they're asking for how the EMF across the coil varies with time. So knowing that the EMF induced, equals to the negative of the rate of change of flux. And students who are familiar with calculus, and I trust all physics HL students are, will recognize that the derivative of the cosine graph is a negative sine graph. And then the negative of a negative sine graph is just a positive sine graph. And therefore, the answer is just A, because choice A is showing the positive sine graph. Question 35 now, they're asking for the RMS value of an alternating current that dissipates an average power that is the same as what a direct current dissipates. It turns out there's nothing to solve for this particular question because the answer is just C. And the reason that the answer is C is because, by definition, the root mean square current is the current that allows an appliance to dissipate the same average power as the appliance experiencing some constant direct current. There's some other equations given in the formula, but it turns out those are just there to this. The choices with twos and the double twos, they're just there to distract you. So it's very important to just know the definition of root mean square current, which I'm going to show you right now. So the root mean square value of a sinusoidal voltage or current corresponds to the value of direct current, well, I guess, or voltage. They will provide the same power as a sinusoidal voltage or current. So again, the answer is just ISO. Moving on, question 36. So the arrangement shows 4 diodes connected to an alternating current supply. So this is about current rectification. Something similar has shown up in past papers, but turns out this particular circuit will give you a very different conclusion compared to pretty much everything that has shown up before this. But in any events, the proper approach is to designate one of the source terminals to be positive, and then try to trace out the path and see whether the top or the bottom of the output will be both positive, both negative. Well, turns out according to, if the left-hand side of the source is positive, then there's nothing through the output, because the top branch is connected entirely in reverse bias. And if you try to reverse the direction of the voltage, then the direction of the current, the current will be through entirely the top branch, and the bottom branch is totally out of it. So in either case, there's no difference and no current through any output that's connected. So this is very different from all the other properly connected rectifier circuits given in all the past papers before this. Now, question 37 involves 4 capacitor setups given, and again, students are meant to recognize how to combine the capacitances. When you have capacitors in parallel, the effective capacitance is calculated using an equation that is similar to how you calculate resistance in series. Actually, that's choice Q. So for choice P, the capacitance will actually be smaller. Choice Q, which has 3 capacitors in parallel. The system capacitance is just a simple sum, so P has to be the lowest and Q has to be the highest. The question does want you to distinguish between R and S. So here you've got 2 C and then C in series. You do the math, and I think you end up concluding that circuit R has a overall capacitance of 2/3. But this last circuit is series but in parallel, so the total C would be half C plus C, which is 3/2C. So circuit Q has the highest capacitance, followed by circuit S, and then R, and then P. So P is lowest, Q is highest. So choice C is the correct answer. Question 38. So photoelectric effect. It's given that incident photon energy is this, and then the metal work function is also given. So this is just an energy conservation question. The formula book does give you an equation. I think Ke max equals to Hf minus phi, which is, I never know whether this should be pronounced as phi or phi, but either way, this is the work function. And the Hf collectively is just 8 times 10 to the negative 20. So this is 3.2 times 10 to the negative 20. In a stopping voltage experiment, the kinetic energy of the electrons are further dissipated by applying a stopping voltage. So the stopping voltage will prevent the electron from completing the circuit. And the stopping voltage can be calculated by dividing the maximum kinetic energy of the electrons by the elementary charge of the electron, which is 1.6 times 10 to the negative 19. So the answer is A. Question 39, which is evidence for wave-particle duality. The four choices are: number one, line spectra of elements. That's actually evidence for the presence of energy, electron energy levels within an atom, so not quite wave-particle duality. B is the correct answer because electrons themselves are particles. Before this discovery, electrons are not known to have wave properties, but when electrons are shown through metal crystals or graphite powder, diffraction patterns were observed, and this supports the fact that electrons behave like waves under certain situations. The third choice, Rutherford alpha scattering experiments, reveal that there has to be a nucleus somewhere within an atom, but that's not evidence for wave-particle duality. And then finally, gamma ray spectra provides evidence for nuclear energy levels, but that also has nothing to do with wave-particle duality. And then the last question now, definition of nuclear decay constant. So how to define nuclear decay constant? Well, it turns out it's just a matter of knowing a definition. It's a probability that a nucleus decays per unit time. Nuclear decay constant is definitely something to do with probabilities and also with time. So it's not A. Well, B itself, the choice B would represent the activity of a sample. And I'll just show you as one last thing from this notes document. There's actually a second definition for decay constant. The decay constant can also be interpreted as the proportion of a sample that is expected to decay over a given time period. And there's definitely a simple issue that I will just fix here. So that completes the analysis of this paper. So hopefully my explanation is clear for the most part. If I have time, then I'll do the second paper. I definitely have time, but I'm not, because this year I have to paraphrase all the questions within this on a separate document, and that's going to be very time consuming. Thank you for watching, and I'll see you guys next time.